Welcome to Molecular Spectroscopy. I'm Dr. Ratan Singh Randhawa, Assistant Professor in Chemistry, Khalsa College, Patiala. I would like to welcome all MSc second year students to first lecture of Molecular Spectroscopy. Let us continue. Welcome to Molecular Spectroscopy. So, molecular, it is molecular molecular spectroscopy. So the topic is molecular spectroscopy, and class, you may understand. So what we will study in this thing, so we will take on UV visible spectra, and we will take NMR, we will take rotational spectra. So we'll take vibrational spectra. So this is UV, means electronic spectra, and I think you are familiar with the UV, NMR, rotational and vibrational spectra. So that means these are what? These are electromagnetic radiation, EM radiations. So electromagnetic radiations, and they are interacting with molecules. So molecules, it may be water molecule, it may be any type of molecule, it may be organic molecule, it may be some inorganic compounds. So we will not discuss inorganic compounds, we will concentrate on the application of these all spectroscopies. So applications, all in organic compounds. So that means we are dealing with this thing. So electromagnetic radiations interacting with molecules. So initially we will concentrate on UV spectroscopy. So it is electronic spectroscopy. Initially just 2 or 3 lecture we will discuss what is UV spectroscopy, and afterward we will move to other spectroscopies. And why UV spectroscopy? Because our first topic is induced quantum transition, or derivation of time dependent Schrodinger wave equation. So if you know about Schrodinger wave equation, so it is minus h cross square by 8 pi square m. So it is curl square psi by curl x square. So it is in one direction. So if you want to add the notations of this, so it is x, y and z. So plus the potential energy, so it is in particular direction, that is x, but psi is in a function of so it is x, y and z, so z. So x, y, z, and it will be equal to minus h by 2 pi iota. So it curls psi by curl t. So this x, y, z we can write. So this t stand for time dependent Schrodinger wave equation. So it depends upon time. So previously we are deriving so many equations, Schrodinger wave equation. We study quantum mechanics, and in quantum mechanics we know this. So is it del, we are using del square, we are using h cap. So there are so many things we are using. So today you'll just look at your spectroscopy book, and that is molecular spectroscopy by Brown. So I will message you that book. So what is the use of this Schrodinger wave equation, and how we know in electronic spectra we know it is A is equal to epsilon Cl. ਇਹ ਜਿਹੜੀ equation है, and we are using this equation number of time, means we are selecting these equations. And what is the significance of this thing? This is epsilon. It is called molar extinction coefficient. So this is molar extinction coefficient. So how to calculate this molar extinction coefficient while interaction of molecules with matter, means electromagnetic radiation ਨੇ ਜਿਹੜੀਆਂ ਉਹ ਤੁਹਾਡੇ ਮੈਟਰ ਦੇ ਨਾਲ ਇੰਟਰੈਕਟ ਕਰਨਗੀਆਂ so interact ਕਰਨ ਤੋਂ ਬਾਅਦ they will have some output. ਉਸ output ਨੂੰ ਅਸੀਂ ਕੀ ਕਰਨੇ ਆ, molar extinction coefficient. We will derive a relation of molar extinction coefficient. So before we derive this thing, you must know somehow of UV spectroscopy. UV spectroscopy is dependent upon Lambert-Beer's law. So Lambert-Beer's law you understand, so it will be in part of your assignment also. So Lambert-Beer's law, and what it depends upon. So UV spectroscopy depends upon double bond. That means there must be a pi bond in the system to be absorbed by a UV spectra, to give a UV spectra. For example, very simple example. So we have C double bond C and single bond C and some C double bond C. So there will be a alternative double bond, such that if you carefully look at this equation, so you can have this type of diagram. So that means if a lone pair of if an electron lies somewhere here and here, they can in the near close proximity, so that they can jump. So if they can jump, they can be absorbed under UV spectra. So that means if a light falls on this, so in the UV region, that means E is equal to h mu, it falls on this thing, so it will have some electron excitation. It may jump to the higher energy state, and that energy state you can absorb energy. So how we can calculate this thing epsilon? So it will help in the time dependent Schrodinger wave equation. So you can see the function eta, it is in time dependent Schrodinger wave equation. So let us solve this equation. So let us solve this equation. So let us delete this thing. So eraser. So this is eraser. Where is? So let us delete this. So time dependent Schrodinger wave equation, and if it is in particular direction, so let us see if it is in a particular direction, so that means we need not to have other components like y and z. So if anything, so it is a wave function, it's a time dependent. SWE Schrodinger wave equation can be rewritten in this form. So it is big psi, and it is x into t. So t stand for the dependence upon time, and x it is in particular direction. So we can add x, we can add y and z in later on stages. So just in case of particle in three-dimensional box, so we can do this thing. So let us solve this equation. So let us do this thing. So if it depends upon time, so let us calculate, let us separate the things. So in this Schrodinger wave equation, so time dependent potential energy will be there, and let us see. So So let us see what will happen. So it is h cross square by a pi square m. So it is curl square by curl x square, and it is also it is psi, so it is xt. So now we had moved to xt, so plus ux potential energy, and it is potential energy is due to the position independent of time, so we cannot write this in the time frame. So it is equal to it is h by 2 pi eta into curl psi by curl t. It is similar to above equation, so it is x into t. So only the way is so we had not written x, y, z coordinates. So writing this, so for the space coordinates in x direction, so how to calculate the probability function? So we know if we write psi into psi star, it will give you probability density. So that means in particular direction, so we can have psi into psi star, and psi star is the you may understand it's the complex conjugate of psi. So here we can see it is a eta term, so it is a complex conjugate of this term. So we have to write the equation, we have to write the solution of this equation also, and we will do the variable separable thing to use this. So let us delete this molecular spectroscopy. Let us remove this. So beta ਹੁਣ ਜੋ ਅਸੀਂ ਕਰਾਂਗੇ, so it is a complex conjugate. So for the coordinates, the probability is given by this, and this psi xg, it is equal to psi x into psi t. So it is written as a phi t, or you may represent as a two functions. That means we can split this thing into psi x and phi t. Let us say this phi is a function of time, and this psi is the function of position. So in that case we can put the equation in the previous equation, that is this one. So we'll have two functions, that is let us put, so it is minus h cross square by a pi square m into curl square, so it is psi x phi t, and it is divided by curl x square plus ux, so it is psi x phi t, so which is equal to minus h, so you remember this thing, so it is negative and same, so it is h by 2 pi eta, it is curl by curl t, it is psi x, it is phi t. So the remember we have two variables, so that is two derivative functions, that is t and another is x. So that means we can separate the things. So that means we can separate the things. So let us erase this, and now we'll use variable separable things to solve above equation. So let us solve this equation. So it is probability density and to solve this thing. So let us solve this thing. So we can write that means this derivative will not affect phi t. So that means minus h cross square curl square m, so it is pi square, so it is phi into t, ਅਸੀਂ ਇਹਨੂੰ ਬ੍ਰੈਕਟ ਦੇ ਇਸ ਸਾਈਡ ਕੱਢ ਲਿਆ, so it is curl square psi x by curl x square, so plus we can rewrite this thing, so it is curl u x, sorry, so it is curl x phi t, so it is equal to minus h by 2 pi iota. Now we can have this curl psi x outside the derivative form, so it is phi t by curl t. Now we had separated the variables, so dividing both sides, ਜੇ ਅਸੀਂ ਇਹਨੂੰ ਉਹੀ ਪੁਰਾਣੇ ਤਰੀਕੇ ਨਾਲ ਕਰੀਏ, the derivation, typical derivation of particle in three-dimensional box, so dividing both sides by psi x phi t, so you'll get psi x and phi t, so if you divide, so you'll get minus h cross square by 8 pi square m, so it is 1 by psi x one by this, so it is curl square psi x by curl x square, so if you divide, so it will be a u x system, so you can write x in brackets, so it is a potential energy, so it is minus h by 2 pi iota 1 by phi t